I'm here with Benno Lossin, who's been working on field projections in the Rust language. Benno, so why don't you explain to people a little bit about your background, and then we'll dive into field projections.
Yeah, sure. So I started out learning Rust in university. It was back in 2021. Maybe like Rust was already pretty developed at that point.
Were you taking classes in Rust, or were you pursuing this on your own?
So we had a networking course, and there we had the option to choose C, Python, or Rust. And Rust was an experimental one that was rather new, and I didn't really like Python, and I didn't want to do C again from my last course. So I decided to try Rust, and I really liked it.
Were people still working out the kinks in Rust in the class, or did it go smoothly?
Well, that was during COVID, so I didn't have too much conversation with classmates back then. But most of them also didn't really try Rust, I think. So.
And how many languages had you learned to that point?
I had learned Java, and I'd learned C. I had dabbled in some other languages, but mostly Java and C.
So not functional programming languages?
Well, no, we had learned that, but I wouldn't say that I've programmed a lot in it.
You didn't program a lot in it?
Yeah.
You had some reference point?
Yeah, we've done Haskell, so I've done Haskell back then, yeah.
How was the experience of learning Rust for that course?
It was, well, you were mostly on your own, but it also wasn't too much to do, so we only had, I think, 4 tasks to do. And I mostly then began to learn in my free time, and instead of doing Java, doing Rust, and having a much more pleasant experience with enums and all of the other features from Rust.
All right, so you learn Rust in this course in university, you start using a little bit on your own. Eventually, you find your way onto the Rust for Linux project in core team, correct?
Yeah.
How did that happen?
So one of my friends was an avid Linux enthusiast, and I was an avid Rust enthusiast. So when we met, we either always talked about Linux or Rust. And then he mentioned to me, I think in around Christmas 2021, that Linux is going to have Rust support in the near future. And I was very intrigued by that, because it was like, oh, cool, I like Rust. Let me take a look. Maybe they're using some cool things. And then I took a look at the code, and I had a bit of a horror moment where I was looking at how they were initializing their mutex. And it was like, you need to first call a new function that's unsafe. And then after you've put your mutex into some allocation, you have to call an init function on that mutex. That's also unsafe. And the reason for that is that the mutex in the kernel requires pinning, because it's self-referential, because the kernel is a crazy place.
Right, so you have a lot of these existing APIs in the Linux kernel that are built in C, and they have, let's say, bespoke requirements that are safety requirements that are written in documentation, not expressed in the APIs. So you see this really unsafe, unattractive API, so what do you do?
Yeah, so I went ahead and wrote a macro for it to merge the 2 initialization functions into one, and to get rid of the unsafe. Because what if you forget to call the init function? Well, you have access to uninitialized memory. And also, what if you forget to, if you have a big struct with like 10 mutexes inside, it's going to get complicated to know which mutex you've already initialized, or which one if you add a new one, you have to remember initializing it as well.
So you're able to just encapsulate the entire pattern in a single macro.
Yeah.
Is it pretty straightforward, or were there any?
No, it was quite complicated.
Okay.
So the first idea that I had was in the beginning of 2022, and then I worked on the solution, posted it to the Rust for Linux folks, and they were very supportive, interested in solving the issue, because they obviously knew that it was a bad API design, but they from their perspective was we need something to work, and we need mutex support, so let's try anything that works for the moment. And that's why they used unsafe there. But they were aware of the issue, and they were already some people that have worked on the issue, and there were approaches using proc macros using syn, and then I built my own one and compared it with the other solutions, and then was invited to Kangrejos, which was very nice to meet everyone, and then we talked about the solution.
Kangrejos is the Rust for Linux conference, which is
yeah,
where we are now.
Exactly. And then over the course of the later part of 2022, we worked together to get the API into a state where it's mergeable into the Linux kernel. And I don't remember the exact time when I had the idea to do this, but in the macro, to check that you have initialized all fields, I'm using a normal struct initializer that just gets type checked, but doesn't actually get run at runtime. So you have like each field that you initialize in the macro gets put into that initializer, and you have a to-do macro as the value for that field.
You have a to-do macro as the value for the field. So
yes.
Presumably you never actually...
You never execute the code, exactly. But it's there for type checking that you have mentioned every field. Mm. So essentially I use the existing mechanism in the compiler to achieve the exhaustiveness check.
Okay, that's clever.
For the struct. And that was essentially the biggest part that enabled us to not rely on syn, because there were other approaches that were more complex. Mm. But essentially that part allowed us to write a huge declarative macro, which we still use to this day. But that one handled that code, yeah.
Nice. So you've been working on field projection. So what got you to working on that?
Basically, it started also at Kangrejos 2022. I was talking
the same year that you
the same year that I went for PinInit here.
Sounds like a productive conference.
Yeah, it was very productive, and the actual idea I had together with Gary. Gary Gu also is on the core team for Rust for Linux, and we together were at a dinner. And we're discussing, because now with PinInit we noticed that it's very infectious. If you contain a mutex, the mutex requires initialization through PinInit, the library that I wrote and presented. Mm-hmm. And to initialize such a thing, the struct that contains the mutex also has to be initialized using PinInit. And then every struct that contains a mutex needs to be pinned. Mm. And then, of course, you need pin projections everywhere, because everything will be pinned. This comes like from the C side, where moving data on the C side is like unheard of. You allocate, and then you free, and you don't move it around. And in Rust, that's a very, very natural operation to do.
Makes sense. So some people will have the either fortune or misfortune of having used like the pin project crate, for example. Did you look into that? Why couldn't you have used that?
So again, we go back to syn. Back at that time we couldn't have syn, because it was way too big to render into the kernel. We only had, I think, maybe a few hundred lines of Rust code in tree.
Oh, okay.
And it landed in the end of 2022, the first part of Rust code. So that's why we couldn't have syn at that time.
It was really early days.
Yeah, really early days. And so now we have revitalized some of the discussion around syn. So maybe we'll get it in the future. I hope so. But back then, syn wasn't an option. And there also is, for those that are aware of, there's a pin project light crate that has a declarative macro. But I think last time I checked, it was multiple thousand lines of code, and it had very bad diagnostics for users. So we decided to say, hey, maybe we can figure out something better that's native to the language as well. And that's why when we first started at the dinner, we said, maybe we can overload the just dot operator for pin and allow access to fields, but that project depending on if the field is structurally pinned or not.
So why don't we start by defining exactly what a field projection is? What would people know in the language that they can relate it to?
Yeah, so conceptually, field projections already exist for references. So if you have a struct and you have a reference to that struct, you can take a reference to any field of that struct. And that already is a field projection. So you turn a reference to the struct into a reference to the field. And you do that using like &struct.field. And for normal references, that works perfectly. But there are other types where you can't access the inner fields. And generalizing to those types as well is what I would call field projections.
And you also want to be able to do it for types other than references.
Yeah.
So I mean, what are some examples of types that's like reference-like types that you might want to use projections with?
So, for example, a mutable reference to a MaybeUninit of a struct, and there you, from a like philosophical standpoint, you can think of such a reference has the ability to go to a reference to a field, but that field obviously is uninitialized because the whole struct might be uninitialized. So you can go from MaybeUninit struct to &mute MaybeUninit field. And now we have the issue that MaybeUninit is a union and has its own fields. So we might not be able to use the dot operator in that case, which is why we relatively quickly thought maybe we want to go and add a second operator to this, because then we are also able to do more things that might not be backwards compatible with just things that are deref, for example.
Yeah, that makes sense. So you've got a reference to MaybeUninit. I imagine a raw pointer would work really well with this also. I imagine you work with raw pointers in the kernel quite a bit.
We also have custom pointers. For example, we would like to have a pointer that only allows volatile operations. If you have something like a DMA, so direct memory access, you would only want to use volatile for accessing the memory location there. Then you want the people to not have to use like a raw pointer and then always care about that you only use like read volatile, but rather have like an encapsulated thing where you can store a struct in that location. Yeah. But you might only want to read a single field or modify a single field, and that would be difficult if you can't project from a volatile pointer of a struct to a volatile pointer of a field.
So that's really low-level stuff. What about moving one level up? So I mean, people will have worked with cell and maybe rough cell. We can use field projections for that too, right?
Yes. So if you have a shared reference to a cell of a struct, again, conceptually it makes sense to go to a shared reference of a cell of a field and only change that field.
Right. If you have a shared reference to that field, you can use the cell API to set the fields.
Yes.
And there could also be that shared reference to cell of the struct coexisting at the same time. And that remains valid because all you can do is just read the entire struct or set the entire struct at once, or read a single field or set the entire field at once.
Yeah.
That makes sense. Let's dig into syntax a little bit. You and I have been bouncing ideas. We've been working together on this a little bit lately. What are some of the ideas that you've had for syntax for this operation?
So very early on, we had the idea to just use the arrow, like an arrow operator, where you have write field, struct, arrow, and then field, similar to how you would use a dot access. And that was the idea for some part. For example, in the first RFC, that was, I think, the main idea. Other people have floated using the tilde operator because the arrow is already known in the C world with a known meaning, and that might be confusing to some people. We had many different ideas about which other sigils we can use in between. So, for example, the .at operator, which I also quite like.
The reason I like .at is I also think it might be nice to be able to write foo.ampersand field as well as foo.at field, not having to back out and put the ampersand in front of the expression.
Yeah. So some IDEs actually put the ampersand before if you want to write a field access. Yeah. So mine, for example, does that, but it doesn't always does it. So it's a bit annoying in that case.
Right.
What I recently had the revelation was that we want field projections to be similar to references. So because essentially we're modeling field projections exactly after what shared and mutable references can do. So we also want to have shared projections and exclusive projections. And there we also need like a way to differentiate the two in the syntax, where I suggested to use the @ sigil in the front and to have like @mute and then my struct, and then arrow or dot @ or whatever option we want to take, and then the field name.
Mm. So you could have the @mute in front and then just regular @ if it's non-exclusive.
Exactly.
Makes sense. Are there any like weird applications in the kernel that you want to use this for?
So of course the kernel, being the kernel, has some crazy things in it. One of those is RCU. It's called read copy update. It's a synchronization primitive that's working in a very crazy way. Effectively, it's a global lock, but that's very efficient for data that's written to only very seldomly. So if you have data that's mostly read-only, but like a configuration, for example, that the user can update through like some syscall or something like that, then it only gets like updated once in a blue moon. And you want to be able to read it very efficiently. Then you can use RCU, and RCU can protect pointers. But it can only protect you from writers. So if you're a reader, you're protected from the writer when you're using RCU. But between writers, it does not do synchronization. So you often use a secondary lock to synchronize between multiple writers. And that's where the problem comes in, because in Rust, you want to have the nice property that the data is stored within the lock, which means that you can only access the data when you lock the lock, which is different from C, where you just have it beside the data. But in C, what you do in the reader case is you don't lock the lock because you have RCU. Now, in Rust, we can't not lock the lock to access the data. And essentially, that's a problem for RCU, because there, in the read path, you don't want the inefficiency of having to grab the mutex, for example. But with field projections, we could make an exception. We could allow you to project through the mutex and get access to the field, but only if the field's type is a special RCU type. So normal types like a usize, for example, you're still not able to access through the mutex. Only if they're stored, for example, in an RCU of box of usize, then you can access it. But in order to read the RCU, you also need to take the RCU lock. So you still have synchronization there, but you're circumventing the mutex.
Interesting. So you've got RCU, which I liken to like kind of a fancy garbage collector for the kernel type of thing, right? Just preserving the data that you're swapping out until all readers are done. You've got the mutex that helps synchronize between writers, and then you've got this fancy projection thing that lets you access individual fields without necessarily having to take a lock. You've been prototyping this in a macro, correct?
Yes.
Can you already do this with that macro?
Partially, yes.
Partially, okay.
So Gary and I had some bouncing ideas around, and he had a crazy idea to use the field name of the struct and take a hash of that, and then use that hash as U64 as a generic argument to a struct that has a const generic, because you can't use strings in const generic. And then that is our is a type that we can use to specify the information of the field on. So that type would then implement a trait that we call field, and then it has an associated type that's just called the type of the field, and then we can set that, and then when we implement the projection, we can in the where clause say, hey, please only do the projections if the field of the type, if the type of the field is RCU of something else. But the problem with that is you don't have access. You can access any field type because we can't make it private. Like it's a public struct in the library, and then if you have a private field, you can still get access to the field type because well, the type itself is public, so you're allowed to access that.
So you like to upstream some of this into the language and into the compiler. I mean, what's the first step?
The first step is exactly getting a proper way to represent fields in the type system. And I've been calling those field representing types. And those essentially take on the role of that struct that has the const generic. And those field representing types you can name them with a macro called field_of, which uses the same syntax as offset_of. But instead of a usize, you get back a type. So you can have a generic argument and you can pass in that generic type in there. And essentially what we want for field projections is to have an operation that's generic over the fields of the struct. And a generic operation is just something that takes a generic, and then we make fields represented in the type system through those field representing types.
And you can write where clauses on those field representing types, right?
Yeah. So obviously we still want a field trait to say what is the base type of this, what is the offset, what is the type of the field actually. And then you can use that as a normal trait bound, like in the where clause where you say, hey, only implement projections if the field type is RCU.
So, okay, if the field type is RCU, are there examples where you only want to implement a projection if the field type itself implements some other trait?
Yeah, so for example, depending on which way we want to go with pin ergonomics, there are multiple different ideas floating around at the moment. So if you want to go in a certain way where you only allow projections if you have a negative implementation of unpin for your type, there you would bound the projection on exactly that negative bound and would say, hey, we only implement this projection if the type of the field implements not unpin or never unpin. And but there are also other cases where you want to have additional information on your field type, but you can't put it on the type of the field because that's user specified. So, for example, if you want to support the normal way that pinning is done at the moment with pin project, for example, where you put a pin annotation on your fields, this pin annotation has nothing to do with the type of the field. It's additional information that you have to track. And this
the pin annotation means it's a field that is structurally pinned within that struct,
exactly.
right? In other words, you can project from a pin of an ambmute struct to pin of ambmute field, which is exactly what you want, right?
And unannotated fields are not structurally pinned, so you can project from a pin &mute struct to just a mute of that field. And to record this information, you need somewhere to put it. And you could have a trait called pinnable field or something, and then you have an associated type that stores which version of the pinning the field has, and then you implement this trait for the field representing type of that field, and that would be very useful also not only for projections.
Yeah, having a type that represents a field and maybe different attributes on that field definitely sounds useful. It actually reminds me of some ideas we've talked about for functions. So every function in Rust actually has a unique type representing that function, and you could imagine bounding these function types with, is a const defin or other properties of that function, supports track color or something like that. It's a really analogous concept.
Yeah.
So you're working on actually implementing these field representing types in the compiler right now.
Yeah. So I have a good mentor, Xiang Ding, who is working together with me. Like, we're having regular meetings. Well, not regular, but we have lots of meetings.
Sporadic, but many meetings.
Well, not sporadic. It's like once every 3 to 6 days or something.
That's good.
But so we didn't make a slot where we do something.
Let's talk about some of the interesting design questions in the space and what you're thinking.
Yeah. So we have lots of design ideas. So the only thing that has been stable since, well, I've been working on this from 2022, And we've had the idea of field representing types very early on. And that has been very stable since then. So I feel like that's like a solid part of the design, and it's proven its usefulness also in other areas. But aside from that, we have gone back and forth between how should the operation look like on the trait system, because it's like an operator, like any other operator that we have until now, and those should have a trait.
Deref, add, subtract.
Yeah, exactly. So we want a project trait for the operation, and the trait probably will be generic over the field representing type that you're projecting, and because you want to be able to change the output type depending on which field you're projecting, that you need that for pin, because there with a structurally pinned field you want to return a pin of that field type. Of the type of that field, and in the other case you don't want the pin wrapping the mutable reference. But then you run into the issue that you want to be able to project multiple fields at the same time if they're disjoint, because you're allowed to do that with mutable references, for example. And that means that the signature of the project function in the project trait can take a mutable reference, because you would have multiple mutable references to the original struct. So at the moment we're using raw pointers, but that's a very unpleasant way to implement the trait. But maybe it's due to the domain of the problem that we have.
So your trait implementation accepts a raw pointer from the compiler, which is basically guaranteeing that it's not doing any aliasing that's incorrect.
Exactly.
But certainly an unsafe function.
Yes.
And then you turn that into maybe a reference, whatever your projection output is.
Yes.
Yeah, it's not a pattern I see a lot in like the core traits where you're accepting a raw pointer.
Yeah.
I actually can't think of any examples off the top of my head.
I don't think like any operation is implemented like that with so much compiler magic going on, essentially, because if we have two different traits, because the one for shared projections and one for exclusive projections, then we also have need a coherence condition between the two. So if you project a field in a shared manner, then you're not allowed simultaneously to have a exclusive projection, because, well, you just projected it in a shared. But you're allowed to have multiple shared projections at the same time to the same field. But you're also allowed to project one field twice in a shared manner and one field exclusively, well, if it's a different field. And so they're like the trait to project a field is probably only allowed to touch data that the field owns, essentially. So you need like this extra condition on the trait itself. So the trait itself also has to be unsafe, because the implementation has to follow certain rules. So it'll be a very subtle trait to implement as well.
Yeah, and it has both invariance that on the inputs that it's accepting from the compiler, and then there's invariance on the implementation itself that have to be, that the compiler is trusting that your implementation upholds.
And also at the moment the project for shared and for exclusive projection, the two traits are identical from except for the pointer that they receive. In the shared case it's a const pointer, and in the exclusive case it's a mute pointer.
And of course,
maybe that's not correct
between those two.
Yeah, you can cast between those two, and you can also have like a shared projection going on while a mutable exclusive projection is happening. So, but from an implementation viewpoint, essentially you're having to implement the same trait twice, and like you also have an output associated type on both, and you both have a project function, but the other is called project mute, because, well, should probably be called project exclusive, because I think it's better to use the exclusive naming for projections, because it might not be a mutable variable that you get out or a mutable reference that you get out.
There are people who have argued that Rust's mutable references should have been called exclusive references.
Yeah.
In many ways for that reason, because Rust has cells, it has interior mutability. But the one thing that you know if you have a mutable reference is that it is exclusive. So you have these two traits. They're more or less identical. They only differ in when they're used. So if you're doing a shared versus immutable projection, and in terms of the output type that you get, right? So are the output types usually like, I don't know, a shared reference versus a mutable reference? Is it always like kind of dual in that way?
Well, we have to see how people will want to use field projection in one way. So there might be specific custom applications where it's very desirable to give you like a completely different type. But from a conceptual perspective, you probably also always are dual, but from a type system that you have different types. So essentially for cell, for example, if you have a ref cell, you are able to project a ref or a ref mute to a field. And in the projections of the ref mute, if you want to project that in a shared way, you have to first downgrade to a ref. And then the output will obviously be a ref. And in the exclusive projection, you're still allowed to have a ref mute to the field you're projecting to. So there you have two different types. But essentially what we've been trying to do as well is to remove like the duplication. So only have one project trait and try to see if it's somehow possible to reduce the design in that way.
It would be nice if we could only have a single trait in many ways. Like maybe you could imagine having a single trait with two output types, but some types don't want to actually implement the mutable side, right?
Yeah. So for example, for cell, I think you only want the shared projection because, well, ampersand cell, I mean, and what would you do with an exclusive projection of ampersand cell? The type is copy. You can't exclusively project it anyway. So it doesn't really make sense to implement that.
Yeah, and I've talked also about the syntax. I think it would be nice if you could write foo at field, but then that leaves the question of where does the mute go, right?
Exactly.
Personally, I think writing foo at mute field is, with a space in between, is not the best, but also not the worst.
I think we'll have to experiment a bit. So if we get field representing types in the kernel, would be happy to have an extra branch where we try things out, and because many people in the Rust for Linux community would like to have field projections for various reasons, RCU, pin projections, because even if we have pin projections for the pin type, we have custom mutex guards. And our mutex pins the data because the mutex already is pinned. So we just structurally pin the data as well. Because we have so much pinned data, we want people to be able to put their pinned data into a mutex. And so the mutex guard has to also support pin projections. So even if you solve pin ergonomics for the pin type, we still have them for our custom types. So we have to have field projections for that.
So we've talked about projecting from a struct to a field of that struct. Are there cases where this can work for enums or for other kinds of types?
So for tuples, obviously, it works very similar to structs because we also want to support tuple structs. And there we already have the work from offset off to support them. And with enums also, offset off has already implemented some work to get offsets of fields in variants of enums. And I think for field representing types, it seems very easy to also support them. We probably need some additional traits to say, hey, this is a field of a struct, because fields of structs you can always project to. And with enums, you first have to check which variant is currently active. But for the projection operator itself, I think for enums, we probably want a new kind of match statement where you can match on which variant is active and then get each field in a projected way. For example, current match expressions actually work like this for references. So if you match on a reference to an enum, you get each variant, and each field is not the type of the field, but actually a reference to the type of the field. And so that would be how they would also work for projections, but you would get the output of the projection type there. But you have to be careful for certain types. You don't have projections for enums. So we talked about cell before. There you have the problem while you're projecting a cell to a field of an enum. Someone else might be able to concurrently well, not concurrently because cell is in a single thread, but at the same time, when you're like in a closure, for example, change out the enum variant under you, and then your field is no longer active, and you have a dangling reference, or rather a reference to a field in an enum that is not the right type. And so you're not allowed to implement it for cell, for example.
Right.
But if you have a shared reference to an enum, then it obviously works because it works today. But if you have like maybe uninit of an enum, there you already don't know if even the variant is active at the moment. So you're allowed to take the projection to the field.
So you can support enums for some kinds of reference types, but not others.
Yeah.
Yeah, I mean, I think people are used to matching on a reference to some struct or enum, and you end up with a reference to one of the fields. It's kind of it's a very natural thing, and it'd be nice if we could generalize that. So if you were matching on a reference to a cell of a thing, you could see through that. So what's next for field projections?
Yeah, we first have to land the PR that's currently open and being reviewed. It has quite a lot of changes, and we have to be careful that we don't introduce anything buggy. But I think
Don't break anything.
Yeah, exactly. If that goes well, then we can have our field representing types, and then on top of that we can implement lots of proc macros to have projections in a unergonomic fashion, where you have to use. So I have a library where you have to use a start projection macro before you can use anything to project it. So that's a bit annoying. And you also have issues with returning a lifetime to the thing that you're projecting down to. So most of the time you only want to project locally in the function, but sometimes you want to return the projected value. And that's not possible because of the internal design of that library. But the compiler obviously would be able to do that because it's a correct thing. It's just that it's difficult to implement, or I haven't figured out the right way to do it. And so experimenting with that library, both in the kernel as well as in other projects, would be the next step. And that's also where people can help. So when we land it in the next couple of weeks or months, then you have a new feature gate that you can enable. Probably not in production, please, but it's also marked as an incomplete feature, so I don't think people will be going to use that. But you also need the library for it to be really useful as a projection, because you only get the field representing types from the compiler at the moment. But then experiment with different versions of that crate, or have other people write one. That would be very helpful.
And then you also want to prototype the projecting traits in the language. Yes. And play around with the syntax, see what the options are.
Feedback on the syntax, for example, is also what would people think is the most intuitive way to express this.
And then once you've got an experimental implementation that is looking good, you've been able to use it, you could open an RFC and we could take you through the linting process.
Yeah.
I think this is a really cool feature. I'm excited about it. I think people are really going to like it when they have this in the language. I think it'll feel kind of like a piece that people didn't know that they were missing until they've actually used it. But I mean, it applies to so many different kinds of types. We've covered a few of them, but I mean, some of these are really fundamental types in the Rust language. They just don't happen to be the built-in reference type, so we don't get this kind of built-in projection operation. Yeah,
I mean, it's a natural thing in Rust to have like a container type that changes something about the contained struct. They most often are wrapper transparent. So, for example, MaybeUninit is maybe the best example, but you could also imagine this for manually drop or unsafe cell, for example. Like these types change certain things about the invariance of what your struct is allowed to have, or references to those to the inner type essentially, and references to those types should behave like normal references, but place special constraints on the fields that you contain. So, for example, with unsafe cell, you would also project through to a field, but not the field type, but unsafe cell of that field.
Makes sense. So really, there's two classes of things that can use this projection trait. There's the types that are wrapper transparent, so they're wrapper around the value, and then there's types that are custom references, or maybe wrappers around a reference that can themselves be projected to a similar reference to the inner value.
Yeah, that's also a perspective that you can take. For example, I did that with the first RFC, where I had two different ways to implement projections, one for those container types and one for custom pointers. But later, I tried to unify them, and I think with the current design, we have only one kind of projection which you can use for both. But we lose certain properties. For example, nesting containers isn't supported. So if you have a cell of a MaybeUninit of a, for example, unsafe cell or something like that, you wouldn't really use that in real life. But if you had 3 different ones, you could nest them. And with the first RFC, you would have had the possibility of projecting through all of that. And you lose that with a new design, but we'll have to see if people really want that.
In practice.
Yeah, in practice. Because I feel like if we can get to just projecting certain container types without any stuff on the outside, for example, just MaybeUninit, that would be great first and foremost. But supporting cell of MaybeUninit would also be an interesting thing.
Well, I really appreciate all the work that you've done on this. I mean, you've been working on this feature for 3 years, and now you're getting to a point where you're landing features in the compiler. So thank you for the work on this, for the design, for the implementation, and really for the persistence and seeing it through. I think people are really going to enjoy the feature when it comes out finally.
Yeah.
And in the meantime, people can help by maybe experimenting with it and leaving feedback, right?
Yeah.
Well, thanks, Beno.
Thanks for
it's
the
been
interview.
great having you on.